Okay. We're going to continue on here with chapter 15. And in chapter 15, we start talking about another equilibrium type of constant, which is known as KSP. SP stands for solubility product. It is, as we talked about, basically the equilibrium constant for things that are technically insoluble based on solubility rules. So again, if we have something like silver chloride, based on our solubility rules, it is going to be insoluble. But anything, even things that are technically insoluble, will actually break apart a little bit in solution and will actually set up this sort of equilibrium. And we can write a K expression for this, which is known as the KSP, which would be our products over our reactants. But when we're dealing with KSP, pretty much this is always how the equation is sort of written. We typically always have solids here on the left and pretty much our aqueous ions on the right. So when you write the KSP expression, it is typically just the products that are included, and we do it like any other equilibrium expression. We use the coefficients as the exponents as well. Now, KSP values are typically very small, and that is because, frankly, they're insoluble. So they typically will stay together there on the left-hand side of the arrow. There's kind of two types of problems that we talked about really involving sort of KSP. And one is if you're looking to solve for the KSP, you basically need to get the molarity of each ion present. And then you could go into sort of the KSP expression to solve for the KSP. You also could, like we did in that one example there, do an ice table if you like. If you are only given the KSP and you're looking for some type of solubility of something like molar solubility, which is our moles per liter, or just solubility, which is grams per liter, you definitely need to do an ice table in this case. Remember that the ice table is pretty much similar to most ice tables that we do. There is a little bit of a difference. We oftentimes will use a little different letter to mix it up a little bit, I guess. Um, so initially here we would have 0 and 0. Our change would be plus S and plus S. And in this case, at equilibrium, we would have S and S. This would go into our KSP expression here, give us S squared is equal to the KSP. And obviously we could solve for S. Now S in this case is really the molar solubility, which is basically the molarity of the compound. We also, like normal, not going to really do anything here in the ice table with our solid since we don't have to use it. Also remember that if you need to go from moles per liter, molar solubility, to grams per liter, that is the molar mass that allows you to do that from the periodic table, grams per mole. In this case, we could do an ice table. And again, as we talked about, when you do solve for the S, that is the molar solubility of really the whole compound. It also is, in this particular example, the molar solubility or the molarity of each of the ions that are floating around. Again, if you did have some type of coefficient, you would have to multiply it by, like I think we did with the aluminum hydroxide at the last example. You do need to multiply it by the coefficient to get the concentration, say, of hydroxide. Any questions on any of that stuff there? All right, so I think that's where we left off, was that aluminum hydroxide. So let's talk a little bit about using KSP values to help us think about what would be perhaps more soluble or what might be least soluble. So when you have salts that basically will produce the same number of ions, for example, here we have silver iodide, which when it breaks apart will give us a silver ion and an iodide ion, which is a grand total of 2. When we have copper 1 iodide, it also will break apart here into not silver, but copper. and iodide. Also giving us 2 ions, and calcium sulfate will give us a calcium ion and a sulfate ion. So the one place where you can use the KSP values directly to compare the solubility of some different salts is when they do break apart basically into the same number of ions. The really reason for that is when they break apart into the same number of ions, you're essentially doing the same math. So regardless of which one it is, it'll basically come out, kind of the same math as you will be doing it there. And the one that has the larger KSP value in that case would be more soluble. Once again, if I have a larger KSP value, it is still an equilibrium value, which means if I have a larger K value, I should mainly have products at equilibrium. And if I mainly have products, those are always going to be the aqueous ions, which means it should be more soluble. If it has a lower KSP value, then that means you basically have a smaller K value like normal. That means you should mainly have reactants at equilibrium. And in these type of reactions, reactants are always the solid guy, which means it will be less soluble and more insoluble. Now, again, you can only do that if you're comparing sort of apples to apples, salts that basically break apart into the same number of ions. Doesn't have to be obviously the same ions, but the same number of ions floating around that solution. Now, when we do have something that breaks apart into multiple or different numbers of ions, we actually cannot use the KSP value to directly compare which one would be more soluble. So for example, here our copper 2 sulfide is going to be a copper 2 and a sulfide, which is again 2 ions. Our silver sulfide, when that breaks apart, will give us 2 silver ions and a sulfide ion, and that obviously is 3. And this guy is going to give us a couple of bismuth and 3 sulfides, which would be 5. So these guys break apart into different numbers of ions in the solution. Now, if we were to go just directly based off of their KSP sort of values, we would actually see that it is the copper 2 sulfide that has the larger KSP value. And it's actually the bismuth guy down here that has the lower KSP value. So you might say that this guy should be the most soluble and this guy down here should actually be the least soluble. And you would actually be wrong in this case, and that's because they do break apart into different numbers of ions. So what you would actually have to do is you cannot directly use the KSP values in this particular case. You got to lay up an ice table and figure out the molar solubility. So you have to run through a calculation, much like we did in the previous examples, and actually figure what is the molar solubility of each of those things. And when you do that, like this table right here, and calculate the actual molar solubility using an ice table, what we actually see is actually the bismuth that's most soluble. And it is the copper 2 sulfide that is the least soluble. So when you use KSP values, you can only use it in a very small sort of way. And you have to be comparing things that have the same number of ions, and then you could use it to decide which one would be more soluble and which one would be least soluble. That is a valuable sort of thing because if you had multiple ions floating around and you want to precipitate out some ions, you could use that to predict which ones would precipitate out first, which one might stay in solution a little bit longer. So we've talked about KSP here, and we talked about solubility. And once again, as I might have mentioned last time, although solubility rules may tell us in certain situations, the sun is bright, tell us in certain situations that no matter what the situation is, when we put these two things together, we should expect a solid to basically form. And that is true in certain situations, but there are a lot of factors that actually can affect the solubility of a compound, can also affect whether or not you'll actually maybe see the precipitate or not. And we're going to talk now about some of the things that can actually have an effect on the solubility of a particular compound. So the first sort of effect that we could have on solubility is our friend, the common ion effect. which is what we talked about when we talked about buffers. And as we talked about with buffers, the presence of a common ion in the solubility of a salt will actually decrease the solubility of that salt. And it's a really simple idea of why that happens is because in these reactions, as we talked about, pretty much we have solid guy on the left and we got aqueous ions on the right-hand side. So clearly, if we have a common ion, the only place where a common ion could be is on the product side, is basically the only place where that could be. And our friend Le Chatelier's principle would say if we have a common ion on the product side, the equilibrium should shift which way? Should shift away from it, right? And it's going to shift away from it off to the solid side and going to keep that thing together. So much like what we saw with the common ion in buffers and things of that nature, we will actually see the acid or base stay together. Here we'll actually see the salts stay together and really not break apart in the presence of a common ion. So to look at an example of this, if we look at silver bromide in just pure water, and the KSP for silver bromide is 7.7 times 10 to the minus 13. So let's take a look at it here together. So if we were going to figure out the solubility here of silver bromide, we would set up our equilibrium with our silver ion and our bromide ion here. Our KSP in this case would be the concentration of silver times the concentration of bromide, and that would equal our 7.7 times 10 to the minus 13. Doing our ice table here, 0 and 0. Change will be plus S and plus S, which means when we get to equilibrium, we will have S and S. Putting that equilibrium into our expression here will get us basically S squared is equal to 7.7 times 10 to the minus 13. We're going to square root there both sides. And if we square root both sides there, 7.7 to the minus 13. Going to give us here, we gotta find the button, 8.8 times 10 to the minus 7. And that would be the molar solubility here of silver bromide in water. Any question on that calculation? So that's very much like what we did previously there. So now we want to look at what is the solubility of our silver bromide if we put it in with a solution of sodium bromide. So first off, sodium bromide is a salt and a strong electrolyte, which means when you toss that sodium bromide into the solution, you will get sodium ions and bromide ions. And when we look at what will set up the equilibrium, it is going to be just our silver bromide in this case, setting up the equilibrium like it did previously inside the beaker. And in this particular case, the common ion here is going to be the bromide. It's going to be our common ion. So when we go to do the ice table, it is going to be a little bit different. It's going to be 0 for the silver, but because we also have sodium bromide present, that is going to give us an initial concentration of 0.001 molar. And that obviously comes from here, 0.001. And it's a 1-to-1 relationship between that and the bromide, which means its concentration is also 0.001. The rest of the ice table here is going to be pretty similar, plus S. And again, this is plus S there on the back end. We're going to go with S and 0.001 plus S. Any questions on that ice table? So it's very similar to the idea of what we talked about if you chose to do like an ice table for a buffer. You got to kind of have the guy on the right-hand side here, kind of the same idea. You need to have the guy on the right-hand side here, as that is your common ion. Again, if you don't have the guy on the right-hand side, you're basically just doing the guy calculation on the left again without it. So you do need to have that. And just like we did there on the left, we're going to go into our KSP expression. So that's going to be S, and 0.001 plus S will equal our KSP value of 7.7 times 10 to the minus 13. At this point, what I'm going to do is this. Clearly, this is a pretty small value of K, as we would expect in our sort of KSP sort of situation. So why not do a throwback to the past there? I'm going to assume in this case that S is equal to 0, since it's going to be relatively small to begin with. Much like when we assume X is equal to 0, we can't get rid of all the S's. It's just going to be, again, the S's we would add or subtract it from a number from. And that would get us down to S times 0.001 equals 7.7 times 10 to the minus 13. We're going to divide this to the other side, and that will get us there. .7 times 10 to the minus 10 molar. You can check it, but with KSP, since the KSP values are typically very, very small, you're usually in a pretty good shape in terms of making your assumption. If you do check it, I don't know, it's like 7.7 times 10 to the minus 7%. So it's a very, very small sort of change that would occur. So when we do compare these things here, we can see that the silver bromide in pure water is more soluble, like we would probably predict. And that is because, again, here with the presence of this common ion, Le Chatelier's principle is going to cause it to shift away from it. And that's going to essentially keep this guy together. And again, obviously, we see a decrease in the molar solubility. And if we took it to grams per liter, it would also be obviously the same sort of thing. We would have a greater solubility there in pure water. Any questions on that there? So the presence of a common ion will basically prevent that guy from basically dissolving. It will keep it in a sort of solid state because of that presence of that common ion. All right, why don't you try one then? Here, let's do a little potassium, no, a little silver chromate. KSP of silver chromate is 9 times 10 to the minus 12. What would be the, we'll go with molar solubility of this compound in a solution with 0.1 molar potassium chromate? We'll go. Okay, let's take a look. So we got some silver chromate, and I got KSP value, which means that is the guy who's going to set up my equilibrium. Again, when it breaks apart in this case, we're going to get a couple silvers and a chromate in this case. That's going to give us a KSP expression of silver. And again, we do need to square it because of the coefficient times chromate here. And that's going to equal 9 times 10 to the minus 12. It's going to be in a solution with potassium chromate. And potassium chromate is K2CrO4. And when that breaks apart, we will get a couple of potassiums and a chromate in this case. And once again, here it is the chromate that is the common ion that we have to take care of in our table. It is a 1-to-1 relationship between this guy and the chromate, which means the concentration of chromate in this solution will be 0.1 molar. So 0, and again, we do need the 0.1 molar there. And again, that's coming from our potassium chromate. The change here will be plus 2s. Once again, we do have the coefficient there, so we do need it. And this will be plus s. This means when we reach equilibrium here, 2s, 0.1 plus s. Any questions on the table here? So we're going to put this into our expression. So that's going to get us here 2s. Once again, we do need to square it because of the coefficient as well. times 0.1 plus S, and that will equal our KSP value of 9 times 10 to the minus 12. I'm going to again assume that S is equal to 0. So that is going to be this guy that gets assumed out. That's going to be me 4S squared times 0.1 equals 9 times 10 to the minus 12. You can take the 4 times 0.1 and then take 9 to the minus 12 and divide it by that. And that will give you an S squared value there of 2.25 times 10 to the minus 11. Lastly, here, a little square root action happening. That's going to give you an S of 4.7 times 10 to the minus 6 molar in this case. Any questions on that there? Once again, if we did the molar solubility of silver chloride, silver chromate in water, we would see it probably be a larger number. And again, it's that Le Chatelier's principle, pushing this thing back the other way and keeping it together. Question on common ion effect here and solubility.